Welcome to this presentation on automated trace analysis. I'm presenting this afternoon with my partner Olaf, and I hope you'll find it useful and informative, and perhaps you'll recognise some of the challenges that we have addressed from your own CANopen projects. Olaf will give an overview of the issues involved, and I will describe how we've been able to address those.
Yeah, thank you for the introduction, Andy. And if I look at the first row right here, Holger Zeltwanger again, what did we discuss yesterday? Reinventing the wheel. Well, we already did it yesterday, and here we are again. So trace analysis is, of course, nothing new to the industry. What changed? Why would we come up with a new system or method to do trace analysis? And of course, once again, we are customer-driven. And when it comes to testing, we already saw yesterday that there are many approaches to what do we test. So yesterday we spoke from the 447 group that you had individual device testing, but now we come to what also Holger mentioned as so important, the interoperability test. So if you really plug in a lot of different devices together for the first time and something doesn't work, well, who is to blame? And you can really see that specifically in highly dynamic systems, this is something that with regular testing methods get pretty complex, because we already yesterday said, well, if after every boot up, the layer setting services are used to assign a new node ID, and with every system start, it could happen that devices have a different node ID, then it becomes particularly difficult to double check who is at fault, who did what in a system. And the challenges we had with the specifically the 447 system is that we can really use fully meshed SDO meshed communication. That really means we have up to 16 devices that each individually can send out a request to every other node. And there's timeouts involved, there's state machines, it could be fragmented transfers where certain states are through. So really, if you look at a trace where at the same time 10 or even 5 nodes communicate with each other, you are lost immediately if you just look at it in the plain trace recording. So you really need help here. It's really impossible to test all combinations. And so where we had the usual CANopen setup where you have one master or manager, one SDO client communicating with all the other nodes, here every node can send individual SDO requests to all the others at the same time. Here's just one live simplified method on how we used it, did a lot of trace analysis in the past, is by manually, with your own eyes, look at it. So what is the easiest, simplest tool to use? Well, load your entire trace into a spreadsheet, Excel or whatever is your favorite, open Office, and look at these, the trace. So you search the trace for, first of all, we need to know who is who. So we would look for the LSS node ID assignments and first see, oh, for this trace, device number 5 is from manufacturer A, and the node number 7 is from manufacturer B. So if we later find a fault, that we know who is who. And something which is quite simple is, of course, what I call here looking for the obvious. That would be emergency messages, unexpected boot ups, or in a system where sleep support is given, if any of the nodes on the network constantly sends sleep objections, and therefore the system cannot go to sleep. Also, in a spreadsheet, you can verify heartbeat timing. If you start using some of the formulas that spreadsheet programs have, you can find all the heartbeats of a different node, calculate the difference and display those. Also, maybe you can do some SDO timeouts. But again, as soon as we have not only a single SDO channel to watch our client, this gets difficult. And also, what about a size limit? I'm not sure how it is with other programs, but for Microsoft Excel, we tried it. It stops after 1 million lines. And for a long trace recording, 1 million lines is quite easy to reach. Then you are out of options. Just to give you an example on what we did in the past, and I spent really a lot of time investigating megabytes traces. And so my original request for an automated tool wasn't so much to have something as a tool to sell. No, I wanted Andy to make my life easier. And that was the main start. And here's just one of these examples where in the top yellow line you see there's an SDO request. Then the red line is a timeout. So here the client who initiated the request did not receive the response in time. And in the trace later we see, oh, there is the response, much more later down here. So we can at this point go back to the manufacturer of that node and say, here, look at this trace, your device is too slow in responding. This is a simple setup. And here, if you're unlucky, it can really be back to back. Here's one of these cases. Well, here's the timeout, but already 2 milliseconds later is the answer. Well, but it was 2 milliseconds late, so the timeout was there. Now, let's review what can we do to automate this analysis. And my approach was that I constantly communicated with Andy and said, you know what, I'm looking at this trace recording, and I really have a requirement. And first of all, my requirement is that I need to find out the truly relevant information of more than 1 million lines of trace, and the input can be really large. And what can you do for me to identify the relevant portions?
So we can feed the CAN bus trace recording into a piece of software that can provide a degree of intelligence and used to identify important and useful events. And we can use these events as an aid to narrow down the search. For example, a node boot-up can be identified as a potentially interesting event. A boot-up could be expected or perhaps unexpected and require further investigation. Node boot-up is a simple example, and a wide range of events couldn't be identified this way, perhaps using analysis of CANopen protocols, such as LSS, to determine high-level operations when something may have gone wrong. And we can even take that a step further. Events can be categorized according to importance, and we can display such events in a filtered way to only show the most severe, for example. Example categories of events could be errors, unexpected events, important things, and general information.
Oh, that sounds great. Can I have it tomorrow?
Yeah,
That's
sure.
my typical answer when he lists something like that. Actually, the next slide is still yours, because the showing the example to it.
So here we have an example of analysis of trace recording, automated analysis. And at this level, we don't see any CAN messages. All we see is a list of events, color-coded to different importance levels. And by clicking on one of these events, it can show us directly the responsible CAN message in the context of the trace recording.
So that already looks as a good start, but of course I have more requirements for you. So we have seen in some of the traces that the LSS node ID assignment didn't work, or the node numbers change. So what can you really do to help me show which device is which in a trace?
Okay, so the analysis module can understand protocols such as LSS. As messages are fed to it, it follows along and determines useful events, such as the discovered identity of a node and which ID was assigned to it. By highlighting these events, it becomes easy to see when the LSS manager was operating and when new nodes were found on the network. For example, consider the case where two nodes are communication partners, for example, a light module and a light controller. If the light module appears to not be working, we can quickly identify through the event log if the light module was found by the LSS manager and assigned a node ID. If it was, then we know the problem is probably in the light controller, and that's why the partnership between the nodes is perhaps not working.
Oh, okay, then let's look at the next requirements. So one of the other requirements, of course, is with boot up and heartbeats. In a lot of traces I've been examining, I've seen that devices suddenly boot up. There wasn't a reset request or anything. So how can I match those?
Okay, the analyzer that we developed is able to identify and monitor heartbeat usage, allowing detection of heartbeat losses. The losses can be flagged as events in the list that I showed before, along with other network management activity. And we can then view the context of the messages that were on the bus around the loss, making it easy to determine if the heartbeat loss is from a missing node or perhaps something else such as high bus load of higher priority messages. It's also possible to detect boot-ups that occur without an NMT reset happening beforehand, perhaps indicating a spontaneous reset of the node. One important aspect that can be automatically measured is the time from an NMT reset to a boot-up message for every single node on the network. And by comparing the startup times, we can see if any of the nodes were unexpectedly slow and require further investigation.
Now, that really was helpful in quite a few cases we looked at, because we found out that some of the devices we had on networks did, in some cases, have a good boot up time, in some cases had a bad boot up time. Because, for example, CIA 447 specifies that the boot up time has to be within 300-ish or so milliseconds. And if a device boot up later after reset and is a fixed, there's other conditions around it, but there are such requirements, and they are sometimes fulfilled on device single tests, but when it comes into operating in the whole network, it doesn't work that well anymore. Also, double boot ups, that nodes sometimes would produce 2 boot up messages. Nobody knew why, but well, happens. So now let's come to the essential part. We were talking about these 15 by 15 or 15 by 16 SDO channels. Now, if we really have that many communicating at the same time and something breaks in there, what really can we do there and show there, Andy?
The analyzer that we developed can understand the SDO protocol. This allows many aspects of the protocol's operation to be measured and checked. For a fully meshed network, or a network where nodes have multiple SDO clients, the use of each channel can be analyzed in parallel to determine the minimum, average, and maximum response times. We can quickly tell if a particular channel or node is generating the bulk of the SDO messages on an entire network by keeping running counts of the total number of requests, responses, and aborts, which might lead to potential optimizations of the nodes and the overall network design. We can also check if there are aborts and mistakes in the protocol implementation, and by understanding the SDO protocol, we can keep track of the largest size of the largest block transfers, and such information allows a systems tester to better understand network behavior.
So also here, some examples, real use cases. We have seen, for instance, that also the SDO timeouts, how fast does a device reply, also differ from a single device test or the complete system, because under load devices simply behave differently. And another fault we also found with this system is that for a segmented SDO transfer, where larger data is split into longer blocks, it would only fail depending on data size. So suddenly you had situations where if you do a device test alone and a standalone test, you only test a few sizes. You don't test all possible data sizes, right? But only on regular operation do you find those. Now, if we look at SDOs, we should of course also look at PDOs. A lot of application profiles have times specified. For instance, in the latest CIA 447, we have specified both an event and inhibit time. As a reminder for those of you not too familiar with CANopen, event time is the cyclic time at which a message repeats. The inhibit time is, well, if the data changes, you are allowed to transmit a message faster, but not faster than the inhibit time. Well, this gives us a really nice measurement window, because now every of these PDOs, we have exact times that we can measure. It may never be slower than, in 447 is I think every 2 seconds, that's the slowest that is allowed, but the fastest often is 100 milliseconds, and it may never be faster than 100 milliseconds. So what did you do to cover all of that?
If we provide information about expected PDO behavior, we can check for out-of-bounds operation. We can count the time between PDOs to determine the event time, and we can check for inhibit time violation, which becomes fairly straightforward. We can also measure the quantity of each PDO to identify areas for optimization, and an analyzer can monitor the relationship between the sync message and synchronous PDOs to determine if any PDO was transmitted at incorrect time, flagging this as an event.
Thank you. Now, one of the more challenging parts after we had this software available is, you mentioned earlier that you need to specify levels of importance. So there is at some point a warning level, at some point you define something as an error, but where do those values come from? So in regards to a heartbeat, if you look at regular 301, there's no times defined, and there's also not defined what a legal variation is. So let's assume you have a PDO configured to go all 100 milliseconds. Well, what is acceptable? Is 105 milliseconds acceptable, or is that a warning, or would we only start a warning at 110 or 115? Well, these are all things to make it flexible. In the software, of course, we need to make it configurable, and in the some of the, I'm not sure if I picked the right numbers here from 447. I think we said that for a heartbeat, it's allowed to have a variation of plus minus 30%, and for a PDO plus minus 10%, but that is then 447 specific. Every other work group or specification would need to review if in their application larger or smaller variations are acceptable or not. So here it really comes down to what the specific requirements in the network are before we flag something as a warning, hit a warning level, or maybe even, well, the error level is typically more simple to identify because of the timeout. The nice thing is, once you start collecting all this analysis data, you of course can also use various graphics to give you an overview. Where does my entire communication and bandwidth go to? And sometimes it's surprising what kind of graphics you get when looking at trace recordings. I, for myself, was most surprised to see that in the 447 system we looked at almost a third of the communication in average came from heartbeats. So really that shows you that there's still a lot of room available for other communication, because the heartbeat coming stable at 200 milliseconds from devices, and the process, the overall bus load we saw never really went much more beyond, I think, 10 or 15%, so there's still quite a bit of room for other communication. But these numbers, of course, can vary a lot depending on the trace you are analyzing. Additional events we get is we can now collect global numbers and look at maximum message range, maximum burst lengths. This is really a value that I like. Although the maximum burst length, I think we cannot do every on all analysis, but what I define as maximum burst length is simply back-to-back CAN communication. And if you measure this in a system, you know this is the maximum delay of your lowest priority message, because as long as you have back-to-back CAN traffic means that any lower priority message would need to be delayed. And if you, for instance, measure for a longer period, well, my maximum burst length was never more than 6 milliseconds, then you know even the lowest priority message would have gone through within 6 milliseconds. So this is really a number I like a lot. In regards to the message rates, I would like to mention that in the latest 447 standard, we now really defined the allowed message rates that a node may produce. And we said, because there's so much communication with the direct connection, SDO connection, there needs to be a certain limit, and somewhere in the standard you'll find the number that we called it a safe plug-and-play device. A safe plug-and-play device may not cause more than so and so many messages per second. And there's then an exception, we defined something higher. It was then a high bandwidth safe plug-and-play device. Also, we can do, besides a global summary, we can do a per device summary. And the per device summary shows us for each and every node on the system, did it have any unexpected boot ups? What was the minimum and maximum heartbeat time? What were the maximum SDO response times? And what's the CAN message rates generated by a specific device? If we look at current implementations, where did we put the software in? We have a pure PC-based software called the Logzaminer, which just takes as an input supporting the popular trace formats that are available and many devices collect, and we can input those. Andy, are there any known size limits by now? Because I remember at the beginning we had to really work on it and to double check that several million lines are not anymore a problem. Do you have any idea what's the biggest is we tried so far, or do you remember?
We can process files of any size. They're split up into 1 million line pieces, but each one can be chosen. Each 1 million line chunk can be chosen and analyzed in turn.
We chose that way to break it down. Because really we came into issues where suddenly we were more hitting the limits of file systems and loading times and stuff like that. So by breaking it down into chunks, it became all more processable. And also just to give you a little bit of an insight, the first tool he presented me took for the first million line about 15-20 minutes to process. So I said, Andy, you please need to look at it. And where are we now for?
Less than a minute for that.
Less than a minute, yeah, that's better. And on the hardware side, we have this also implemented in our live diagnostics tools. So you can do both live monitoring of CAN networks and get these event lists, or do a pure software log. Well, and that we are a little early at the end, but that gives more room to the others or for questions. Thank you.
So I come close to you to share the microphone. So are there questions from the audience? Seems not the case for the moment, so I have to admit it's not that easy for a session chairman when you ask already yourself the questions. You have always to think about some new, but first of all, one you didn't answer, so did it make your life easier now?
Oh yeah, it did.
Okay, and you said...
No, actually, the problem is we can now charge less consulting hours to our customers. Or I simply say, oh, I did look at it manually.
Okay. So maybe one final question to you. So you said there's the possibility of an offline analysis, of an online analysis. Can this tool, if you are active with an online analysis, also interfere the system in a way that it sends you or comes up as a CANopen node, let's say, and says, hey, I detected some faulty tendencies here and can inform the host controller?
No, currently this specific monitoring mode is purely passive, so it's just monitoring, of course, the after analysis anyway, but also in the live system it's doing pure monitoring. However, the event list of what happened is generated in the background and displayed. So as an event happens, a red line might flag up, and with each red line you also get a beep or something, so that you know something happened and I can now look at it.
Okay. So thank you. So some further questions from the audience, please. Okay, as I said, so you asked a lot of questions by yourself and answered them. So thank you very much once again.
Thank you.